Welcome everyone. So this is our 54th live stream geometry. We have 3 people here with us. So if you'd like to join future sessions, feel free to email me at mgreenb801@gmail.com. It's in the description of the video. It's on Sundays at 8 a.m. US Central Time. So today I'm going to go over the USA team selection test. So in the last sessions, I did the TSTST. So that's the selection test to make the team selection test, but this is just the final team selection test for the US to decide who gets to go to the IMO. So with that, I am going to share my screen in just a second. Here we go. All right, so here's the first question. So it's 2 circles and their common tangents. I kind of like problems like these because I feel like we don't do that many of them. So we have 2 circles. I'll try to make them not overlap, although I don't think it really matters. And we want to draw the external tangents, and they meet at point T. I want T to show up on the screen. So maybe I could do it like that. Maybe make A a little smaller. Maybe like that. And okay, so this is point T. I'm going to hide the internal tangents in just a second and make everything look nicer. Hide that, and we need to rename a couple things. So, okay, so we'll call this one gamma 1. So it touches, so one of the lines touches the first at A and the other touches the other at B. So this is A, this is B. Might as well, I'll just call I'm gonna hide these points right here. And I could call the centers O1 and O2, I guess. Or I'll just do P and Q. And let me hide. Actually, you know what? Let me just draw that. Just going to draw these as line segments. We don't want to call that C though, because there's already a C. So we could call this F, and we could call this G maybe. All right, that looks better. So we have a circle that passes through A and B. So it could be any circle, and it intersects this circle again at C and the other circle again at D. And here's where it gets interesting. So we see, whoops, I don't know where D went. Oh, I think I just hid D. So we let AC and BD meet. So I might want to make this look a little better. Maybe like that. So AC and BD meet at X, and AD and BC meet at Y. AD and BC. It's a little hard to see, so I'm going to move it. Let me see. I can change this. Oh, because I hid the other point D, so I think that's kind of making it a little hard. But maybe I could just do something like that for now. And so this is X. All right. So it looks like we have someone new just joined. Let's see. Hi, Ida. Thanks for joining. So that's point X, this is point Y. So this is our first problem. So you haven't missed too much. So Ida, where are you from? If you don't mind sharing your country. It's all right. All right, so we want to show that T, X, and Y are collinear.
This looks like Brocard's theorem.
Brocard's theorem. Yeah, it does look a little bit like it, right? Because the way it's set up.
So if we let A, B, and C, D meet at a point, then we should prove that T lies on the polar of that point.
Okay. So let A, B, and C, D meet at a point, and then X, Y is the polar of that point, right?
Yeah.
All right. Okay, so XY is the polar of E with respect to the circle ABCD. And what were you saying about we want to show E lies on the polar of something else? T lies on the polar of E. Yeah. Okay. Interesting. Let's draw the polar, see what that looks like. I mean, obviously it's just a line, but the line TXY. So I don't know if it helps to draw the polar of T with respect to the circle, and we want to show E lies on it. So we know AG is the polar of T with respect to this circle, and BF is the polar with respect to this circle. But I don't know if that helps with this circle. Let's see. That is an interesting problem. So as we move C around, what happens to X and Y? They just stay on a line through T. Yeah, so I guess really, yeah, we don't even really need X and Y. You just need point E, and then we could show, we want to show T lies on the polar. It's a good way to do that. So we could try to draw the tangents from T to the big circle. And then maybe use harmonic, like find harmonic quadrilaterals or something. let's see. I draw the tangents from T to this circle. I wonder if there's something special about point E. Like maybe there's like some cyclic quadrilateral or something. Yeah, let me get rid of point P in that. We'll take E, T, does that pass through that point right there? I think that's probably a coincidence, but let me check. ETC and that point. It's hard to see. It's hard to tell. Serdar, but I don't think that's cyclic. Hey Serdar, thanks for joining. So we're still on the first problem. So this is the USA team selection test. So yeah, it seems like a simple problem, but yeah, I'm not sure. And it feels a little bit familiar too. I feel like we might have done something like this before. I don't know if it was this exact problem or not. I mean, so yeah, I think I kind of like the idea of trying to show that E lies on the polar of T. But I'm thinking of another way. Like maybe we could drop perpendiculars from X and Y to these two sides and show that the ratio of them for X is the same as for Y. Maybe there's some similar triangles. I don't know if triangle TAY is similar to TXF. Let's check it out.
Can you intersect EX with AB?
EX and AB?
EX.
Okay. Oh, TX, or wait, TX you mean, right? Sorry, TX. Hey, Dat, thanks for joining us. So we just started on our first problem. So let's see what that looks like. So call that H. So yeah, we don't know they're collinear, but we're kind of assuming they are, and then maybe there's something special about point H.
Maybe we can try to prove that EHAB is harmonic.
Oh, yeah, no, that's a really good point, because if EHAB is harmonic, then T lies on the polar of E. No, I like that. Like, what if we did this? What if we Well, because we don't know that these are all collinear.
Yeah, we will ignore y, and we will try to prove that
Okay.
h is not.
Okay, so we can kind of ignore y for now. We show that EAHB is harmonic. I kind of like that. Whoops. We can hide those points. So yeah, if we show EAHB as harmonic, that solves the problem. And where should we project through? Probably point D, right? So if we project through point D,
You draw the midpoints of AF and GB,
sure.
and then connect them.
So draw the midpoint of AF and GB. Are I, X, and J collinear?
Yeah, they are. From radical axis theorem.
Okay. Because yeah, it has the same power.
So can you name the midpoint of AB?
AB. Okay.
Yeah.
AB. All right.
Our aim is to prove that CD KH is cyclic. Then we are done.
CD.
CD KH.
CDAH. That doesn't look cyclic. Oh, CDKH. I'm sorry. I thought you said CDAH. Yeah, sorry if I understand something. Apologize. Okay, so we want to show CDKH is cyclic. Yeah, I'm actually still trying to see how that solves it. Oh, okay. So EC times EB. Okay. So wait a sec.
So we want to prove that A times EB equals to EH times EK.
EK. That makes sense. This is a really clever idea. Yeah. Okay. So we want to show CHKB is cyclic. Is angle CHK 90? I don't think so. But I'm going to check it. No, it's not 90. But maybe, I don't know if triangle ACH and KJB are similar. No, I don't think so. Let me check. Actually, I'm not sure that's not the case. Whoops. Nah.
Is
Yeah.
ET, BD cyclic?
ET, ET, what were the points?
Okay, it's not.
Oh, sorry, ETBD. Yeah, thanks for writing in the chat. Yeah, sorry, I get the letters wrong. I'll try my best to get it right when you say it. Okay, so we want to show EAHB as harmonic. We could try projecting through. So what if we let BH meet AX at a point? And we want to show AC and X are harmonic with that point. Yeah, inversion.
In similar center, similar center, and the centers form harmonic bundle. Maybe we can use that.
The in center, the in simila center and X simila center.
Yeah, and the centers.
And the centers. So those 4 points form a harmonic bundle.
Yeah.
Let's see. It could be useful. I'm not going to draw that. Well, yeah, just because the circles are, the way I drew it, the circles are really close to one another. So it's hard to see the in simila center, but we can think of how to do it, then I'll draw it in. Maybe we could let TI intersect TE intersect IJ, and then we want to show IXJ and that point are harmonic. Or we could try showing a cyclic quadrilateral that you said. So LIXJ.
Name the circumcenter of ABCD.
Okay.
Then draw MT.
Okay.
MT.
Oh,
Not
sorry.
T.
MT. Okay.
Drop a perpendicular from E to MT.
Oops. Oh, that's perpendicular bisector.
Now draw the circumcircle NMB.
NMB?
Yes, NMB.
Okay.
And that should pass through that point, yes.
Okay.
Oh, well, that is sufficient.
Oh, that would solve it. Okay. All right, let me delete the stuff I added. Make it a segment. Okay. So I guess another way we could say it is we want to show that NMBL is cyclic. So if we could show CHDK is cyclic or NMBL is cyclic, either one would solve the problem. But yeah, is there another point on that circle? Let's see. Maybe there's something special about this point. I don't know. Maybe not. Oh, are O, G, and N collinear? No, if we can prove that, then that would solve the problem. So yeah, we're trying to prove that. It's not obvious that they, okay, O, G, and N are not collinear. All right. Yeah, I'm gonna hide that circle. Yeah, we want to show B, M, and L is cyclic. Okay. And MNE is 90, so I wonder what a diameter of that circle is. So if we extend NE, we would get a diameter of that circle. So I don't know if we draw ML. Is there anything special about this? Oh, it's going to be tangent to the circle. And then if we drew this one, it would also be tangent. So maybe we could use like harmonic quadrilaterals or something. So if we let it intersect at this, So TL times TB, you draw those 2 points. Maybe it's worth drawing this point, because then we could show that NMOA is cyclic. Wait, if NMOA is cyclic, because O and A are both on a circle, so that and M is the center. So MOA is isosceles. So we want to show MOA is MNA, which would be the same as MAO, which means that so M is going to be, if we draw the circumcircle of MOA, M is the midpoint of that arc. Let's see. So what if we drew the circle with diameter TM? Let's see. Yeah, it would meet at, I think these are concurrent. So that's kind of interesting. Yeah, okay. So this is going to be like the point of tangent C of T with that circle. If the problem is true. Yeah. Oh, that, yeah, and that would be equivalent to just showing that E lies on the polar of T. Yeah, there's a couple different ways to do this.
Michael,
Yes.
could you let ID cut CB? Yeah, could you show the point Y?
Oh, yeah, I can show the point Y. Hold on a second. Whoops. There we go. All right.
Okay, so we could project to prove that TYX is collinear.
Okay, so I'm gonna. Do you need point H for your solution?
Yes.
Okay.
Yes. So hold on. Let me tag if we could prove.
Okay. Yeah, take your time. Okay.
Okay. So if we if we could prove this, so t y and x is collinear.
Okay. So you want to show
Right.
that the cross ratio of those four lines AT, AH, or AT, AY, AH, AX is the same for B.
Yeah.
So how do you define H? Is H the intersection? Well, I guess you don't. It's really just those four rays, right? So you don't.
Yeah, just for rate. X. We don't need. Actually, we don't need H. Yeah. Just replace A, B, and BA. Yeah.
Okay.
Yeah. We need AT, AY, AB, AX is equal to BT, BA, BH, and BX. BY and BA and BX.
Okay.
So if you could if you let AD cut the circle at one point and AB cut the circle at one point.
Okay. Hold on a
Yeah.
sec.
Yeah.
AB and AD.
Yeah, AD. Yeah.
Okay.
It already cut. Yeah. Cut. No, the smaller circle.
The smaller circle.
Yeah.
Okay.
Yeah. Yeah, and BC and BA. BC and BA cut the bigger circle.
Okay.
Yeah.
Sorry, let me move the letters.
Yeah. Move the letter K. Yeah.
There we go.
Yeah. So if we could prove that so if we project onto the circle and so AT, AY, AB, and AX will become A, U, S, and C, right?
Yes.
So and the same with B. So we need the ratio UC over UK times AK over AC is equal to WD over WV times BV over BD.
Okay.
Yeah, and we use sign because you see UC in UK is sine CAU and sine KAU, right? Which is sine CAD and sine DAB. The same with WD over WV. That is sine DBC over sine CBA.
Okay.
Yeah, and the last thing we need is proof that SA is equal to VB.
SA is equal to VB, and that's by power of a point, probably, right? Because KS times, or you might have another way to do it.
I don't sure that PowerPoint proves that. We only have
So I guess or I'm sorry, go on, or go ahead.
Yeah, and we need SA is equal to VB, and I still have to prove that.
Oh, I can prove that by power of a point, because like if you look at point K, it lies on the radical axis of those two circles, and so KS times KA is KV times KB, but KA is equal to KB, so that proves it.
Okay. So because K is the midpoint of AB, right?
Exactly, because K is the midpoint of AB.
Yeah. So SA will equal to VB, and that will solve the problem.
All right. Yeah, and there might be another way to do it too. That's just the first way I saw it. Okay. So, all right. Spiral similarity can also be used. So are you saying spiral similarity can be used to, instead of signs? How would you use, is ACUS similar to DWVB?
I'm not sure about that.
B over CK equals to BC over CB.
Okay. So did you say CA over CK is, could you write it in the chat? Yeah, thanks. I appreciate it. All right. CU over CS is CB over CB. Okay, so those two are similar. Okay, so all right. Hold on just a second. There we go. Okay, so let's see the, actually, did we ever use point E?
We don't need point E in my solution.
Okay. All right, so we can calculate okay, so projecting onto, okay, so we have that is equal to so T,
I think we should replace H by B.
by B.
B. Yeah.
And then that's A U K. No, I'm sorry. A U.
2 points are gone. Where are they?
Oh, I must have hidden them. Sorry. Oh, did something go away when I deleted stuff? Maybe.
Yeah.
Yeah. Okay. I'm just gonna hide point E instead of deleting it.
Yeah.
There we go. Okay. So we have check the chat. Okay. So that's going to be A U. Where did H go? Oh, B. We got to replace it with B. Sorry. So A U S C.
Yeah, AUSC.
I'm going to make this look, I'm going to fix this up in just a second. I just want to keep it in my head. Okay. So AUSC, and then we have B of TYAX. And that will be B, sorry.
Yeah, it should be BW, V and D.
BW, okay, BW, VD.
V, yeah, VD. Yeah.
And then AUSC, So you had an idea using sines, and I think Serdar had an idea using spiral similarity, right? Let's see. So I wonder, like, let's say you take AUSC and you project through A onto this, you would get IX. Oh, but we don't know where U goes. Okay.
Yeah, we don't have that point. Yeah, so yeah, I think we could use sine.
Okay. All right. So I'll use sines. So we want to show CU. So this is CU over US divided by CA over AS.
Yeah. So UC over US.
And then divided by AC over AS.
Yeah. That would be AS. That would be times AS over AC. Yeah. Yes.
And then for this one, it would be WD over WV. Times B BV over BB.
Yeah.
All right. To the right. So like this. Oh, see what I'm typing? Yeah. Sorry. Yeah, I don't know why GeoGebra doesn't let you move the box that you can type in, but that would make it easier and smaller. Okay. All right. Maybe that'll help.
That would be much smaller. So we
Yeah, I'm gonna make it bigger in the end. I'm just making it smaller so that when I type for now, he can read it.
Yeah, okay.
Just show B and F. There we go.
Yes.
Okay, so we're gonna try to use sines to show that these are equal.
Yeah. So UC over US is sine of UAC over sine SAU.
Okay.
Yeah. Yeah. Times AS over AC. Yes. And yeah, and sine UAC is sine DAC.
Okay.
Yeah. And sine SAU is sine BAD. Yeah. Yeah. Times AS over AC.
Okay. So, okay, DAC over BAD.
Yeah, DAC over BAD is CD over BD. So that would be CD over BD. Yeah, CD over BD times AS over AC. Yeah, and the same with the below one, which the below one will have CD times BV over BD times AC. Yeah, and we need to prove AS is equal to BV.
Okay. I see someone just joined on their iPhone. Thanks for joining. Although I don't know if they just got kicked off, but okay. It's weird. I don't see them anymore. Okay, so CD over BD. Sorry. Sorry, I don't remember what you just said. So, what do I say? What do I do after this? Do I just do the same thing right here? So this is,
Yeah, after, you should do the same thing. And
Okay.
at the end, it will be CD over AC times BV over BD. Yeah. Then
BD over BV, like that?
No, BV over BD. Yeah, BV.
BV over BD.
Yeah, and if BV is equal to AS, the problem will be solved. Yeah.
Okay, interesting. So, all right, so I'm gonna make this look nice now, or as best as I can. Wow, this is a really cool solution. So, all right, so we have that. Let me break it up into a couple lines. What? I don't know why that didn't work. Try this, that. There we go. And I'll just say by a similar calculation. I'll just skip to the very last step because well, actually, you know what? I'm gonna put like, just say this. All right. So we have this. Whoops. All right, I'm gonna make the diagram bigger now. So, whoops, sorry. Oh, looks like Urajan is joining us. Hey, Urajan, thanks for joining. All right. Let me move it even a little more now. Okay. So then we want to show that AS equals VB, and okay, so we could do it my way using point K. I don't know if there's another way to do it, but I mean, I guess that way works. So I'll just say define U, V, S, and W as shown. So we have that. And then I'll say I, J, and K actually. Or let I and J be the midpoints of AF. And let I, J, and K be the midpoints of AF, B, G, and AB. So I, J, and K are linear. And then an IJ is the radical axis. I'll say whoops. Y on a radical axis. And then, okay, so we have KS times KA equals KB times KB. And KA equals KB implies AS equals BB. So, oh, why does K, because, so KI and J are collinear because they're the midpoints of AF, AB, and BG, and we have like AG is parallel to BF.
Yeah, we should just say that AG is parallel to BF.
Yeah. Since AG is parallel to BF, yeah. There we go. Okay. So yes. So we have so these two let me just do this. And so since those are so combining the above, we have a TYBX is equal to B of TY colon AX. And that implies TY and X are collinear. All right. This is a nice solution. So yeah, Sardar, if you can find that way to do it using spiral similarity, yeah, feel free to put it in the chat. So you said you have to prove AU over AB equals BW over WC. Interesting. All right, so I'm going to move on to the next problem because we're already an hour in. But this is a fun one. Whoops, didn't want to do that. Just wanted to move on to the next one. Cool. All right. This one looks like it might be a little easier. I'm not sure. So we have a triangle ABC. M and N are the midpoints of AB and AC. Whoops. That's M. And this is N. So then we draw the circumcircle of ABC. And X, okay, so we draw a tangent to it. And then here's a point X. And then we draw MX and NX. So we draw the circle through M and B, tangent to MX. And then through N and C, tangent to NX. So let's see how this works. So I'm gonna want to draw basically the perpendicular to MX through M and see where it meets the perpendicular bisector here. And that will be the center of the circle. I'm going to clean this up a little bit later, but okay. And then I'm going to do the same with N. And then I want...
No, you don't have to do that. just let the circle cut BC at the point and draw the circle NC in that point. Let that circle cut BC at one point, circle with center D.
Okay.
Center D. Yeah.
So this
Just,
circle?
yeah. Cut BC.
BC, sorry.
Yeah.
Oh, basically I'm using the problem to do it. Yeah.
Yeah.
Makes sense.
Yeah.
All right. So.
Yeah, and now you could hide.
All right. Let me make this look a little better. So, whoops, I want to draw a segment.
Oh
We
no, just draw the line, so you could see where X move.
Okay. All right, and okay, so if I move X this way, yeah, they're not tangent. I don't think that. No, the circles aren't tangent. Let me make it a taller triangle. There we go. That looks better. So, yeah, maybe something like that looks okay.
Draw the circumcircle of AMN.
Okay. Maybe it's past. Oh yeah, because by
Because of
Michel's
Michel's theorem.
Yeah.
Yeah.
So a homotopy about A with factor 2 would take this to the whole circle. So maybe I'm trying to think what's a good way to do this. Maybe I could just draw one of the circles, like, and So basically, like, let's say I just drew one of the circles and it intersects at point F. I want to show that that's the same point as it would be with the other circle. Maybe that's one way I could do it. And then by Michel's theorem, that would solve it. Maybe I could draw the center of this circle. I don't know. It'll help. So yeah, MN is parallel to BC, obviously.
Maybe we can use some of the segments.
The sum of this.
The circles cut BC at different points. Then we will try to prove that sum of the segments equals to BC.
Equals BC. Okay. So I could just draw one of them for now. So
maybe we can calculate BH.
Okay. So we know BM is half of AB, and yeah, BH.
And can you let MH intersect AC?
MH intersect AC, yes.
JXMA is cyclic.
A,
Angle choosing.
all right. Oh, and they meet on the circle too. That's interesting. Oh yeah, I'm sure it can be vast with complex numbers. Yeah. Let's see if we can find a synthetic solution. And yeah, if it is cyclic, like I wonder if it follows that these
intersection
circles.
point is obvious.
This intersection point, yeah. Is that just Mikkel's theorem again?
Yeah.
Okay. Is AJ BH? No, I don't think so.
XF looks like it is a tangent to AMN.
XF. It does look like it. Let me play around with it a little bit. Interesting. That's cool. Don't know why yet, but yeah, because we know XA is tangent, so we want to just show XF is also tangent.
Probably better to define it like it is tangent and then show for one of the circles that circle passing through it is tangent.
Yeah, because basically, yeah, if we define F to be the tangent from X, then basically if we could show that that's cyclic, that would solve the problem because it would be the same argument for point C. So I'm guessing it's probably an angle chase to show that JAM X is cyclic. Sorry, Vanch was asking in the chat, or JAMK. Yeah. Well, is XM, is that true that XM is tangent to BFM? I don't think XM is tangent, is it? Oh, Serdar. So you guys think it is. So, whoops. Let F
It's
be.
given in the problem.
Oh, whoops, my bad. Yeah, it is given in the problem. That's silly me.
If we define F as he said, then we will have a symmetric one. So we need to just prove that for one circle. So it's
Exactly. Yeah. So if we just define F to be the tangent, then we want to show that BHMF is cyclic. I'm going to hide this circle for now, just because so I forget, how did we define H? Oh wait, I think we needed the circle to define point H, right? I think we just yeah, I think
actually, we just want to prove that BFM equals to X and B. So we don't need H if we.
Yeah, we don't need H, right? We just need to show that this circle is tangent to. We want to show the circle BFM is tangent to XM, right? Yeah, sorry, or John, I know you said that earlier. It's in the chat right here, but yeah, my brain is just trying to figure everything out. Okay.
You delete K.
Okay. Do you want to delete the circle right here?
Yeah, you can. We won't use.
Okay. So we have tangents to two different circles. This is kind of interesting.
Can you let BF intersect the circle of AMN?
Yeah. Like this?
Yeah.
XM? Oh, you want me to draw the whole line or see where it intersects the circle? Okay. Yeah. All right. Let's see. So can we use an angle chase here? We want to show XM as tangent. That's the same as saying angle XMB is MFB or BMF. There's a couple ways to think about it.
Let D let define the midpoint of AF.
AF?
Yes. Oh, I think actually that solves it. So I will explain what my thought was.
Okay.
So we have that angle FMJ is equal to AMX because of the symmedian theorem.
Okay, wait, FMJ is AMX?
AMK.
AMK, yeah.
Yes. And we see that M is the midpoint of AB and K is the midpoint of AF.
Ah, that solves it,
So,
yeah.
Yes.
I like it. That's a really nice solution. Okay, I'm gonna hide this. I'm just gonna draw AX for now. And I'm gonna start writing this up. So, okay. So let the tangent from X to the circle, let F be the foot of the tangent C from X to AMN. Yeah, that's really nice. So, yeah. I don't know if I'm going to have room for the text and the picture, but oh well. Let F be the foot of the tangent C from X to AMN, different from A. And let K be the midpoint of AF Yeah, I'm unfortunately when I'm typing, we could show that JH is parallel to AB. Interesting. So that's like another way to do it. All right. I'm gonna just finish typing it up this way. So let K be the midpoint of AF. Then by the symmedian theorem, angle AMK equals angle MFJ. So yeah, I'll just say it by the symmedian theorem. MJ is a symmedian in triangle. I think is it MFA? And that means that angle FMJ equals angle AMK. Which is equal to angle ABF and so that implies that XM is tangent to BMF. And once we know that, that means that the circle BMF is the circle omega B. Is omega B in the problem. And then similarly, CNF is omega C. C in the problem. And so by the converse of Mikkel's theorem, BMF and CNF concur on BC. I'll just say omega B and omega C concur on BC. All right, nice solution there. And I will move on to the next one. So it's 10:20.